Okay, I think we can start. Good afternoon, everyone. Welcome after the semester break. Our first seminar in this semester will be delivered by Dr. Weronika Narloch. Weronika graduated with her PhD at CAMK Warsaw. Then she spent some time at the postdoc in Concepcion in Chile. And now she's back to Warsaw, and she's a researcher postdoc at CAMK. Working in Araucaria group, and the floor is yours.
So, for those who might not know the Araucaria group, this is a group which is mostly interested in measuring the distances in the universe, and as well improving the methods of measuring distances. I work with Professor Grzegorz Pietrzyński, who used to work here at the university. Now he's in Nicolaus Copernicus Astronomical Center. So, period-luminosity relations are one of those kind of cosmic measures. They are based on the idea of the so-called standard candles, which is very nicely presented by this graphic in the background. So, topic variables are pulsating stars, which are one of the so-called classical pulsators. These are the stars which occupy a very specific region as a fractal cluster diagram, which we call the instability strip. First such a star was observed in 1784. That was the Delta Cephei, from which the whole class of the variable stars took the name. Many years later, the Henrietta Swan Leavitt, the lady, one of the computer ladies in the Harvard University, hired by Edward Pickering, she was working with the data first from Small Magellanic Cloud and later Large Magellanic Cloud. And she made a very interesting discovery, which we can read from the paper from 1912, that a remarkable relation between the brightness of these variables and the length of their periods will be noticed. So in Small Magellanic Clouds, attention was called to the fact that the brighter variables have the longer periods. And then later, they also made a statement that a straight line can really be drawn, thus showing that there is a simple relation between brightness of the variables and the periods. So the brighter the star is, the longer is its period. And that is what we know today as the period-luminosity relation. It became very useful just a few years later, because in 1918, Shapley incorporated a different type of variable stars, error Lyra stars, at that time all known as a cluster variable because they were mostly discovered in global clusters. He incorporated it into his calibration of Cepheid period-luminosity relation, and he used that as a tool for measuring the distances to global clusters and also to estimating the distance to the center of the Milky Way, estimated because of the size of the whole galaxy. This gentleman is known also from a different very important event which took place on 26th April, so soon there will be anniversary, 1920. There was a great debate between Shapley and Curtis. They were discussing about the nature of the nebula objects which were observed and catalogued by Messier. Curtis was in favor of the idea that these are actually separate galaxies outside our galaxies, while Shapley actually thought that these are objects inside our galaxy. This debate was not solved for the next few years until Edwin Hubble, another astronomer, in 1924, he observed Cepheid variables in the Messier 31, one of those nebula objects. And using those separates, he estimated the distance to this nebula and noticed that the distance is much larger than known size of the Milky Way. So it cannot be a galactic object. It has to be a separate galaxy, very much distant from us. The gentleman is known for yet another discovery, which he published in 1929, because he used this method also to calculate the distances to all the galaxies. Also, he got the radial velocities from the spectroscopy of those galaxies. And when we put those two values on a plot, it turns out that there is a relation, another line relation between the distances and velocities with which the galaxies are moving away from us. We know that relation today as the so-called Hubble law, or more recently, Hubble-Lemaire law. The proportional coefficient here we call the constant, Hubble constant, or rather Hubble parameter. Hubble constant is just the value of parameter at a given time. And as the Hubble wrote for himself in the paper, it represents velocity at unit distance and can be interpreted as the rate of expansion of the universe. And we can also infer the age of the universe out of this constant. Hubble estimated it to be 500 kilometers per second to megaparsec, which already at that time was quite a suspicious number, because it would be resulting in the age of the universe shorter than the age of Earth, which was already known from the fossils. Nevertheless, the great discovery of Hubble, or actually in case of this is just a confirmation, empirical confirmation, is that first he expanded the size of our known universe, and secondly, he experimentally proved that it is expanding even farther. In 1944, Walter Bader, for the first time, resolved the stars in the center of M31, which we already know this is a galaxy, more widely known as an Andromeda galaxy. And this observation led me to define distinct populations of stars, population 1 and 2. And he also divided Cepheids into two populations, because one type of Cepheids belongs to the population 1 and the other one to population 2. And he noted that population 2 Cepheids are actually about 1.5 magnitude fainter than Cepheids from population 1 at a given period. This division of Cepheids allows him to correct Cepheid distance scale by doubling the distances, and also corrected the Hubble constant to be now around 100 kilometers per second per megaparsec, which is the value much closer to the one we know today. And although we still don't know the exact value, and there is actually in cosmology something which we call the Hubble tension. There are different methods of calculating this value, and the more precise we measure them, the less they agree. So Araucaria group, as I said at the beginning, is interested in improving the distances and improving the methods for calculating this distance. Among the methods, the most precise are the geometrical methods, isometric binaries, or parallaxes, because the source of the parallaxes is Gaia mission nowadays, or eclipsing binaries. The problem with geometrical methods is that they cannot measure very large distances. They are good to find within our galaxy or perhaps local group, like eclipsing binaries, for example, and one of the most famous results from Araucaria group, the distance to the Large Magellan Cloud. But they can be used much farther. But for example, period-luminosity relations to Cepheids could be if we will calibrate them based, for example, on those geometrical methods. And then, if we would like to measure even further, then we need to use another method which could be calibrated based on the previously calibrated method. And this is how the cosmic distance ladder or cosmic distance scale is built. So about the period-luminosity relations, we prefer to use them in the near infrared, and this is not surprising because they are the steepest there. We have the smallest problem with the reddening. We have the smallest dispersion. However, in the title of this talk, I told you that we are going to do that in the Sloan band. Why and what are actually the Sloan bands? This is a photometric system, which is a wide-band photometric system covering all optical range. And it was for the first time developed for the Sloan Digital Sky Survey. And since then, it became very popular among large-scale sky surveys like the Panoramic Survey Telescope and Rapid Response Pan-STARRS, the Dark Energy Survey, or last but not least, 10-year Legacy Survey of Space and Time, which is going to provide us with a huge amount of data that would be quite a goldmine to explore if we will have a proper tool. And this is quite surprising because field relations in the Sloan bands are still studied in the literature. So that was the gap in knowledge which was used, which Araucaria group decided to fill. And then they applied for time on robotic 40 centimeters telescope, which are part of the Las Cumbres Observatory Global Telescope Network. This is a network of telescopes distributed around the world on the southern and northern hemispheres, which allow us to observe the objects on both hemispheres. And in principle, we could observe one object continuously when the telescopes from different parts of the world will just take over the observation, right? We were collecting data for about 2 years in 3 Sloan filters, G, R, and I, and we calibrated them using Atlas Reference Catalog version 2 to the Pan-STARRS version of the Sloan photometric system. Pan-STARRS will be the one which will be used by the LSST. With Sloan photometric system, there is kind of a problem because it's not like with Johnson that we are just using Landau standards and we're all in the same page. No, each of those big surveys, they have their own version of the Sloan photometric system. So this is very important to note which one we are actually using. Yeah. Okay, so our observational campaign started with the classical satellites, and the results of which were published in 2023. Then we continued with Lyra stars, and we published the results in 2024. And then we ended up with type 2 satellites. The work is submitted and is up to second review already. This is an example of the light source we obtained for our classical satellite. Different colors mark different telescopes which were used to observe a given object. The scheduling of observations, the responsible person for scheduling the observations was Gergely Heinrich from our group, and he really put an effort to populate as well as we could the light curves and obtain a decent number of points for each star. We had like between 30 and 50 points per star. In case of satellites, sometimes we had more than one in the field, but for example, they were observed just by chance because there was a main object in the field and the other stars were just because they are there. So sometimes we can find not so beautiful light curves, but just because they were not the main objects. Let's move to the sample of classical satellites. We had 96 of them, all of them pulsating in the fundamental mode. So we are not interested in first overtone. We were quite bright objects. The Gaia magnitudes were between 6 to 12 magnitudes. And the plot is showing the distribution of those stars. Not surprisingly, we can find satellite variables in the galactic plane. The distance was between 0.6 up to 12.5 kiloparsec. It also, this larger distance is also because of those by chance targets. And we got the quite decent range of periods between 3 and 69 days. This is an example of period-Besenheim relation, where the Besenheim indices, they should be reddening-free by the construction for a given reddening law, and they were defined by Madova in 1982. The open circles are the stars which were rejected based on the quality check from Gaia, this Gaia Ruve and goodness of fit parameters. And the crosses are stars which were rejected based on 3 sigma T. In the paper, we investigated 2 approaches of calculation of reddening vectors. We used them, the ones from the work Leavitt Law 2019, and also calculated them directly from Fitzpatrick Law 1999 for the comparison. The comparison with the literature, in this case, was pretty tricky because that simply didn't exist. Our relations are first of their kind for the surface in our galaxy in Sloan bands. But we found the theoretical work from Dickinson Total 2013 in SDSS system, actually. These are lower panels. And in the upper panels, this is a comparison to empirical relations from Coleridge et al. 2018, which is all in pan-star system, but in N31. And on the left panels, we have relations using the reddening vectors from Green et al., while on the right-hand panels, these are the ones from the Fitzpatrick. And we decided that, yeah, seems that actually Fitzpatrick is performing worse. So in the future works, we use just the reddening vectors from Green et al. So, yeah, okay. Let's move to the Araucaria stars, with which I encountered much more problem during the analysis. The surface variable turned out to be quite easy. I had many stars, they were pretty nice. But in case of the Araucaria, there were some new problems I was not aware about. We were observing 53 stars, 44 of them of RRB type, which are stars pulsating in the fundamental mode. And they are marked with circles here, and 9 of them are C type stars, which are first overtone and marked here with squares. The distance of those stars is much different than Cepheid because all of them are closer than 3 kiloparsecs. And the distribution errors we can see is also much different. They are mostly from the halo of the galaxy. And range of periods is less than 1 day. And this is analogous period based on height relation for Araucaria stars, but this time on the left panels, I'm showing the calibration of relations for RLC and RB type stars separately, while on the right-hand panels, this is for the combined sample, where RLC type stars had to be moved towards the RB type stars in the process of fundamentalization, for which I used a very common formula just by shifting the RLC type stars in the logarithm of period by the constant number. However, it seems that it actually is not aligning those 2 populations of stars, the 2 types of stars properly, but rather it's introducing some kind of systematic error. And this, we are not first to notice that. It actually was noticed before, also by Zgierski et al. 2023, also another work from Araucaria group, in the near infrared. And in that paper, the author decided to take another approach for the fundamentalization. Instead of using this constant number, they used it as a free parameter during the fit and derived it for each filter separately and present like magnitude, claiming that it is aligning those 2 types of stars much, much better. We also repeated that in our paper, but later, during the conversation with Professor Moscali from Copernicus Center, he introduced me to a paper of Nemec et al. 2024, and it complicated my view on fundamentalization even more because it does the sample 0.127, which is actually logarithm, right? It's corresponding to the period ratios of the first overtone to fundamental of 0.746. But it turns out that in RRD type stars, which are pulsating in both modes simultaneously, this period ratio versus the fundamental period, it is not a single number, it is rather a quadratic relation. So in principle, we could use such a relation that corrects the fundamentalization shift for each star separately. We used all those 3 approaches in the paper, but it turned out that we had just 7 stars because 2 of them were rejected based on the Ruppel parameter, and it actually was not influencing the result almost at all. Nevertheless, for the distance purposes, we actually recommend to use RRB and RC type stars separately because clearly there is some problem in the fundamentalization and it might introduce systematic errors. In case of Lyra stars, there was literature to which we could compare. However, only the globular clusters. And honestly, we got a very different 0 points as well as the slopes. And we think that there might be at least several factors which might be the culprits in this kind of comparison. So the comparison with theoretical work from Saceres and Catalan is showing one of the possible problems, which is the helium content. They are investigating those colorful lines, such like different alpha to iron ratios, how they are influencing the 0 point. It actually might influence them quite a lot. And this ratio might be different in different environments. Globular clusters are more homogeneous environments, while our sample is much more heterogeneous. Also, recently I counted the paper where it was the work done in Omega Centauri, very specific globular cluster with a large range of metallicities, and they were looking for helium enhancement in the function of metallicity, and it seems that there is such a relation. So helium content in the stars from different environments might be might have an influence on the 0 point of the period-luminosity relation. The comparison with empirical relation from Setter et al. 2017, which was derived from 5 globular clusters, is showing or suggesting yet another possible problem, which is the metallicity range we use for the calculation of period-luminosity metallicity relation. Setter et al. Had something like from -1 index up to -2.3, something like that. And as you can see, those red lines actually, between different bands, it is not changing the slope, which is weird and against our intuition. The PL relations, they should be steeper towards rather bands, as is actually happening with our relations. In our case, we had a much broader metallicity range from about 0 to solar type up to -2.6. Another possible problem is by comparing ourselves to globular clusters is shown on the example of relation from Vivas et al. 2017, which was derived in N5. Those two dashed lines are their relation, but using different distance modulus for the cluster to calculate the absolute magnitude. And as you can see, it is influencing the 0 point. We are using parallaxes from Gaia DR3, which are quite precise for such close stars as Lyra stars from our sample here. All stars are closer than 3 kilopascals. But the truth is that we do have a small number of stars, and so we don't have a very good statistics, unfortunately, comparing to the literature. But what is really the problem? Honestly, we don't know. It should be investigated. Of course, it came to our mind that, well, maybe perhaps something is wrong with our photometry. So we used the photometric compilation from Watson et al. 2017, as well as virtual observatory spectral energy analyzer to analyze the spectral energy distribution of the stars common with the compilation from Watson et al. 2017. And okay, this is the result from FOSSA, which is not very well seen probably, but we can see that the red dots are actually the photometry from Monson, while the orange dots is our photometry. So there might be some, and this blue line is the fit, yeah, and there might be some bigger disagreement for the G band, which is not surprising. This is a blue band, and the reddening laws have the biggest differences in the blue regime. But in general, it looks good, probably except this one star B675 Sagittarius, which it seems that our photometry is systematically fainter than what we expect it should be. So we marked this star in the paper. So if you wish to use the photometry for it from us, just be careful. Yeah, but it seems that photometry is okay. So the differences we see between us and literature, well, the mistake in photometry or is not explaining that. Okay, honestly, I'm not sure if this is working, so I don't know how much time I have. Is it working? I'm okay.
1, 3, 4.
Ah, okay. So let's move to the type 2 satellites. This work is submitted, not published yet, but already after the second revision. So the results which I'm going to show you are accepted one. It's just other things which have to be corrected. We were observing 39 stars, and after reanalyzing the light course, it actually turned out that within our sample, there were 16 fully typed stars which have shorter periods. Yeah, in our case, shorter than 4 days, and they are marked with circles. 17 of them turned out to be W Virginie type stars, marked here with squares. And then it turned out that one star was actually a first over from Sapphire. 3 stars were peculiar W Virginies, and 2 of them were of early Tauri type star. So BL type stars in our sample on average are closer than W Virginies. W Virginies are the ones with much longer periods, which will be important later in one of the plots. Okay, this time I'm showing you period-luminosity and period-boson height relation, because I would like to draw your attention into a new kind of symbols. These are those red crosses. These are stars which we decided to reject manually because they were not rejected by the 3 sigma clipping. And now I would like to explain you why we actually decided to do that. This is a zoom to the period-luminosity relation, and let's focus now on AUP among BL group type stars and Leavitt Law from W Virginie. When I will switch to period-boson height relation, you can see that they actually do not deviate anymore. If the boson height is actually reddening 3, it would mean that something wrong is in the reddening of those stars. If we check the polar versus logarithm of periods, as well as the magnitude diagram, we clearly see that the Leavitt Law is way too blue. So it's probably over the redden. AUPAC is too red. So we tried different reddening maps, because in this case we used the Schlafly and Fick Biner 2011 integrated using the model of the galaxy. However, they did not resolve this problem. So okay, we decided let's reject those stars. Now we look at the Araucaria, which is lying below the relation, and it is lying below in both cases. This star is a kind of mystery, because in Wielgórski et al. 2022, where there was presented the relation in the near infrared, it was behaving exactly the same way. When we check the color magnitude diagram, it seems that the star is fainter than other W Virginie stars. So maybe, perhaps, something is actually wrong with the parallax of this star. We don't know, because again, this doesn't seem to be the reason of the reddening, right? We decided to reject it. Also, Piotr Wielgórski, in his work, he also rejected this star. So we just followed his steps. And then we are left with V410 Sagittarius and Scuti, which you see they also deviate in the case of boson height magnitudes. And when you will look at the polar magnitude diagram, it becomes quite clear that those 2 stars are just overluminous. And these are 2 stars the most farthest away in our sample. And we are just thinking that it must be something wrong with the parallax of those stars, because they have strangely large distances. So we also rejected them from the field. Okay, we also could compare ourselves with the literature, again, only from the globular clusters, because our relations are first for type 2 surface from the vicinity of the sun in the Sloan bands. And again, we don't get a good agreement. It seems like it's working better in case of Bevan height relation than period-luminosity relations. So we decided to check. Okay, let's check another reddening, because maybe something is wrong here. We used two of the maps, Hilisma and Biostar 2019, and these are those dashed lines. However, okay, the result is a bit different, but still much closer to what we obtained with Shapley being binary than what actually Leavitt obtained in the globular clusters. So again, we don't know what might be the reason here. But in case of the type 2 satellites, we could also try to check our relations using type 2 satellites and 31 from the work of Copernicus 2018. So in case of Copernicus, they do not provide relations for type 2 satellites in their work, which I think is quite wisely done. Okay, we just use their surface reddened to calculate the Bevan height indices. We used our relations for both PL Hercules and W type stars, fix the slope and use the 0 point as the free parameter. And what we obtained by this is the black line. We got the distance modulus to M31 24.0 magnitude. While Leavitt Law 2021 did the number of 24.407. This is the distance. This is also calculated based on surface, but classical surface. And the Greece and Bono from 2044, they were recommending the value of 24.46. So we get a very large difference. But if we use the division between RB Tauri type stars and W Virginis type stars, for example, from the work of Soshinsky et al. 2011, which is 20 days, then it turns out that actually in our sample of, not our actually, but the Kodrik sample from 2018, majority of stars are of RB Tauri type stars, which we were not having in our sample. And also, Soshinsky et al. 2008 actually mentioning that it is not good to make the global solution for all type 2 surface, because RB Tauri type stars do not behave linearly in the optical regime, but rather they have they curved. So what we're doing here by fitting our relations to the mostly RB Tauri type stars in the Sloan bands, we are like overestimating the magnitude of our relation and underestimating the distance to the galaxy. If we will use exactly the same relation and we will fit ourselves just to the W Virginis type stars, we get the value of 24.253 magnitude, which is closer to what we would expect, but still not close enough. We can still use relation from our work, which was defined only for the W Virginis type stars without PL Hercules. And then we get 24.255. Again, very similar number. So what's going on here? We think that we are actually having a problem of selection effect. So we see in M31 stars, which are just the brightest ones. And the fainter W Virginis type stars, we don't see. So what we do, we just, again, overestimating the brightness of our relations. Also, we see the stars which are like in M31 closer to us are brighter than the ones which are on the other side of the galaxy, more farther away, fainter. So again, this is like we do not calculate the distance actually to the center of the galaxy. So this exercise actually is not showing that our calibrations are wrong. It's actually showing the difficulty of using type 2 surface as the distance indicators. Of course, they are very useful when we do not have surface and classical surface we would prefer, but we have to be aware of many difficulties. Okay. This is a summary of all our pulsating stars. We perform the calibration period-luminosity and Vezan height relation, as well as period-luminosity metallicity relations in case of Araucaria stars. For pulsating stars from the vicinity of the sun in the Sloan bands, and for all of them actually for the first time. Classical surface, pulsating in the fundamental mode, were published in 2023. Araucaria stars last year, and type 2 surface are submitted. This work was submitted. So, as for the future, we are already actually using 80 centimeter telescope, ZD telescope, named after Zbigniew Kołaczkowski, one of the astronomers who's working for many years in Wrocław and later joined the Araucaria group and passed away a few years ago, unfortunately. And this telescope is this one, not good pointing with the finger, but the one here on the side. Placed in Weronika Observatory in Chile, which is an observatory belonging to the Nicolas Copernicus Astronomical Center. Our goal is to obtain better coverage of the lighthouse, which might be useful for also other projects, like, for example, the lighthouse templates. We plan to obtain already observing a larger number of variables, mostly from the southern hemisphere, of course. And what is really important from my point of view, we are obtaining uniform data from 1 and not 16 telescopes. It was pretty tricky to put all that onto one page, and it's limiting actually the quality of the light curves. Also, those 40 centimeter telescopes are actually not cameras, right? Big cameras. They were suffering from the non-linearity. We found a way to deal with that, but still, it is introducing not necessary uncertainties. Here we will have uniform data from the instrument that we hope that we already know well enough to reduce our data. And that would be all I prepared for you. Sorry.
Thank you very much.
Maybe just one remark also that this image is also taken by a telescope from our observatory, telescope in the Sloan bands.
No settings. Any questions or comments? Radek, I can see your face.
So I'll ask a question. Right. So one number that was missing for me was how accurately you actually can calculate the distance, assuming you have Cepheid or classical Cepheid or type 2 Cepheid or large stars with photometry in 3/10. Like, what's the accuracy of the distance measurement based on period-luminosity relations? And at the end, you mentioned the future plans with OCM, and the question is how much better you will do once you get better data from OCM.
Well, okay. So I don't know if this error is answering the first part of the question, but that's.
But for Cepheid, you do better?
Yeah, for Cepheid better, because in case of type 2 Cepheid, this I think is answering the second part of the question. Unfortunately, we do not have many stars, 16, 17 W Virginis, 16 BL Hercules. So we really hope to obtain better sample. As for the surface at this very moment, oh, I don't remember how many, but I think it's about 200 we are observing, with Araucaria stars over 100. Indeed, type 2 surface, unfortunately, I am afraid that we do not have that much larger sample, but indeed it will be at least doubled. So we hope that we will get better statistics and smaller errors on the coefficients. In case of type 2 surface, should at least go down twice.
Anyone? So I was wondering, because you said that you were taking the Gaia parallaxes for granted, and for those systems that actually found out that probably the parallaxes are wrong, that didn't fit the relations for the loose wave. Have we check any other like parameters in the Gaia, like some of the flags or some of the numbers that are given by the solutions or some errors? Is there any correlation like?
Well, the errors of the parallax
I mean, there's like this parameter, there are some like quite a lot of them. Maybe it's worth to take a look. Maybe it's an indicator for future that
because the parallaxes, of course, they were corrected using Lincoln correction. In this case, we also were checking to the Lincoln corrections, but the difference was not that much. But it, more than and because of speed and the error of the parallax, it's not checking. What else could be the good here?
Well, I don't know. I was just wondering
Okay,
how to
well,
eliminate, you know, not as you said, waste time on observing the target that doesn't fit. For which you cannot have like a proper data.
Ways in time, well, it's not that because it is okay. It might not go to the Copernicus relation, but it might go to the template. So it's not that wasting time, but indeed, you're right. That probably, I don't know. We have to wait for Gaia 4, I think. Maybe it will answer our question. I hope it will, because I don't have any other idea what we want to do.
We have anything on Zoom?
No, I didn't see any rising hand.
Okay, I don't see also one raising hand here. So thank you, Veronika. Thanks a lot. So it's great work. And next week we will also listen about the variable stars. There will be double eclipsing binaries by Jakub Kolasz from Masaryk University in Brno. And two more announcements. The notebook, that's one of the things, so please put your names. I don't know if you already did. And the other thing is that from this semester, we don't have to like put money for the suites that are given. So thanks to the decision of our director. Thank you very much.